In this module, we will discuss electrical circuits. So, electrical circuits can be found in most of the electrical equipments. For example, they are inside your laptops, they are inside your phones, and in most other electrical gadgets these days, you will find electrical circuits. And there are some basic components of a circuit. There are some quantities that a circuit work with, some physical phenomena, and there are some components of circuits. We will discuss this in detail in this module. So first we will begin with current, which is the flow of charge in an electrical circuit. Then we will talk about resistance, which is the obstruction to the flow of charge in a material. And then we'll talk about power sources, which could be, for example, batteries that basically power our electrical devices. Then we will talk about another component called capacitors, which basically can store electrical charges. And then we will briefly discuss electrical safety. So let us begin with the definition of electrical current. Electric current is the rate of flow of charge through some region of space. Current has the unit of ampere, ampere denoted by a capital A, and ampere is basically coulomb per second. Remember, coulomb is the unit of charge. It's coulomb per second means the amount of charge flowing per unit time. And current is denoted by the symbol capital I. So let us obtain an expression for the average electric current flowing through some area. So in this picture you see a circular area of magnitude A, and there are positive charges moving perpendicular to this area. So suppose in a time delta t, the amount of charge that flows through this area is given by delta q. Then we define the average electric current, I average, as the ratio of delta q over delta t. That is the amount of charge flowing, delta q, in a time interval delta t. Now this is for constant current. What if the current is instantaneous? That is, the current is not constant but changing over time. Then we need to define the instantaneous current as the derivative dq over dt. That is the rate of flow of charge, and it is shown in this expression here, I equals dq over dt. Then what is the direction of the flow of current? You may think current is basically the flow of electrons, so it should be directed in the direction the electrons flow. But that is actually not the case, because from the beginning we have used some conventions, and we still follow those conventions these days. So current is defined as the flow of, the direction of current is in the direction of the flow of positive charge. That means the current is directed opposite to the flow of electrons. In most materials, it is actually the electrons that are carrying the current, the flow of electrons. It's not actually the flow of positive charges when we talk about electrical currents, basically. So the current is defined in the direction opposite to the flow of electrons. And we will be talking about a charge carrier also. Charge carrier basically means a particle that has some charge that flows in a particular direction. For example, electrons or positive ionic charges that can flow in vacuum or some other in vacuum tubes or some other devices. But over here we will mostly restrict ourselves to the flow of electrons. Let us now define drift speed. Drift speed is some average speed with which the charge carriers flow in a material. Why do the charge carriers flow in the first place? You need to have an electric field applied to the material or the device. So if there is an electric field, the electrons will move opposite the electric field. And you can also think of positive charges moving in the direction of the electric field. So this electric field causes an average drift velocity of the charge carriers. And now let us work out the relationship between current and drift speed. So we will begin by assuming that there is a wire of cross-sectional area A, as shown in this figure, and suppose there are n number of carriers within some length delta x. These carriers are flowing perpendicular through A in a time given by delta t. So the drift velocity, as you can see, can be defined as delta x over delta t. But let us first start with the number of charge carriers that are flowing through A in a time interval delta t. So this whole volume, all the electrons that are inside this entire volume, they are flowing through this cross-sectional area A in a time interval delta t, right? So the number of charge carriers per unit volume is assumed to be n here, and then what is the volume of this cross-sectional area, that is shown in gray. So this is given by delta x times a. So the total number of charge carriers that are flowing in a time interval delta t is given by n times a times delta x. Now what is the total number of charges flowing? So you have to multiply this number of carriers by the charge of each carrier, which is given by q. And we know from the previous slide, the drift velocity is the distance traveled, drift speed is the distance traveled over the time interval delta x over delta t. So then we can write delta x in terms of the drift speed and delta t, and then we substitute this into the expression for delta q, and we obtain something like this. Delta q equals n times a times vd times delta t over q. So this is this gives us the total amount of charge flowing in a time interval delta t through the cross-sectional area A. And we have assumed that there are n number of carriers per unit volume, and they are traveling with an average drift speed of Vd. Now to obtain current, we have to divide by delta t, because remember the average current is delta q over delta t. And we get this expression for I average, which is equal to n times q times a times Vd. So number of carriers per unit volume times charge of each carrier times the cross-sectional area A times the drift speed Vd. So that gives the average current flowing in this wire. Now, so we have looked at the average motion of the carriers, but how do the motion of carriers look like in general? Like, I mean, not in an average way, but how do they move in reality? So in reality, they don't move in a constant direction, but they actually move in a zigzag manner. This schematic shows an electron moving with a drift speed of Vd against the direction of the electric field E, and you can see the electron is moving in a zigzag manner, abruptly changing its direction of motion. And why is this happening? Because as the electron moves, it makes collisions with various entities in the material. For example, it could collide with other atoms that are in its path. It could collide with other electrons that are also flowing. It could collide with lattice vibrations also, for example, which you will learn in a higher physics course. So there are many factors. Let us assume that the electrons are colliding with the fixed atoms in the lattice, and they are changing their directions abruptly like this. But on average, the electric field is enabling the electron to flow with some drift speed Vd. Notice that it is the electric field that is driving the electrons to flow. So if you apply a higher electric field, then the drift speed will increase. But in general, the drift speed is quite slow, because because there are many collisions the electrons are making with the atoms in the lattice, for example. But what we see in everyday life, for example, it seems to us that the current flow is very fast, right? For example, if you turn on a light switch, instantly, when you press the switch, instantly the light is turned on, basically, right? So it happens in an instant. So why does this happen? Actually, what happens is that electrons are not flowing from the switch to the light, because that speed, the drift speed, is very small actually. But what happens is that it's the electric field that reaches from the switch to the light. So the electric field, so there are already a lot of electrons in the wire. You can think of the light connected to the switch by a wire, and there are already many electrons in the wire. So when the switch is turned on, the electric field pushes against all these electrons, and the electrons which were already near the light, they already reach the light, basically. So electrons on the side of the switch do not have to flow all the way through the wire to reach the light before the light is turned on. So it is actually the electric field that goes instantly from the switch to the light, and that kind of pushes the electrons that are at the other end of the wire, basically. So a good analogy is to think of a water pipe. So Suppose there is already water in the pipe, but the tap is not turned on, and now you turn on the tap, so the water enters the pipe, but this water is not flowing all the way to the end. There's already water in the pipe, and the water at the other end comes out almost instantly, right? So you can think of the same analogy for electron flow in this case. So the important point to note is that the electric field travels very fast. In fact, it travels almost at the speed of light, basically. And that's why when you turn on a switch, the light is turned on instantly, basically, even if it could be located far away, basically. And the same in all electrical devices in our homes, basically. The same concept applies. So let us summarize what we have just discussed. So electrons do not have to travel from the light switch to the light bulb in order for the light to operate. The electrons are already in the light filament. They respond to the electric field set up by the battery or the power supply. And the battery does not actually supply the electrons, it only establishes the electric field. So when you apply a power source, it could be a power socket connection from the power supply, electrical power supply, anything. So that is establishing the electric field. It's actually not supplying the electrons. The electrons are already there in the wires and everything. But it's setting up the electric field that creates a drift speed for the electrons. And this electric field travels very fast through the wires, almost close to the speed of light. So this slide pictorially shows you the analogy between electrons flowing in a copper wire and water flowing inside a pipe. Microscopically, you see that the electrons undergo many collisions with the lattice. Sometimes these are referred to as scattering. And but on average, they are traveling with some drift speed Vd, and that depends on the magnitude of the electric field. And the analogy is similar to the water flowing in a hose, as I have just explained. So what is the magnitude of the drift velocity, the drift speed, for example? Suppose you have a copper wire with one free electron contributed per atom to the current. So the drift velocity for a 12 gauge copper wire carrying a current of 10 ampere is about 2.2 times 10 to the power minus 4 meter per second. And so what is the speed of light? The speed of light is 3 times 10 to the power 8 meter per second. So you see that this drift velocity is very, very small compared to the speed of light, basically. So the electrons are actually flowing very slowly inside the wire, but the electric field that the battery is producing, that travels close to the speed of light and instantly reaches the other end of the wires. Now we will talk about a very important law that describes current flow in many materials. It's not a general law, so it doesn't cover all the materials, but it covers a good subset of the materials that we use in our electrical circuits. And this is called Ohm's law. So what it says is that for many materials, the current produced inside the material is proportional to the electric field applied. So most of the metals actually obey Ohm's law. That means if you increase the electric field, the current will also increase and increase proportionally. This is also related to the actual potential difference that you apply to the circuit. So the more the electric field, the more the potential difference, the larger is the electric field. So the potential difference and the current are directly proportional. The more potential difference you apply to a circuit, the more current that flows through the circuit. The materials that actually obey this Ohm's law, they are called ohmic materials. But there are also non-ohmic materials, because Ohm's law is not a general law. It only applies to a certain set of materials. The materials which do not obey Ohm's law are called non-ohmic materials. And it is important to note that Ohm's law is an empirical relationship only for certain materials. So it's not generally applicable, but it explains current flow in a variety of materials. Now we come to this other topic, resistance. Resistance is the obstruction to current flow. So it is given by this expression, delta V over delta I. Delta V is the voltage difference or the potential difference and the current is given by I. So the ratio of the potential difference or the voltage over and the current is called the resistance. So if this ratio is large, then there is more obstruction to current flow, as you can see. This comes from Ohm's law, as we have seen basically. So in Ohm's law, we mentioned that the potential difference is proportional to the current, and resistance is actually this proportionality constant, and resistance is denoted by a capital R. Resistance has the unit of ohms. 1 ohm is defined as 1 volt per ampere. So because R is defined as, resistance R is defined as delta V over I, so the unit is volt per ampere. So 1 ohm is defined as 1 volt per ampere. And what is actually resistance in a microscopically? Can you explain resistance? So remember, we mentioned that when electrons are flowing through a material, they are undergoing collisions with the fixed atoms of the material. So this actually explains the origin of resistance. This is why there is resistance in the material, because I mean the atoms, when the collisions occur, these are basically obstruction to the flow of the electrons. So the higher the value of the resistance, the more the number of collisions, and the slower is the drift velocity, right? If there are more collisions on the way, then the drift velocity will be slower for that material. Let us look at another definition of resistance, and this is linked purely to geometry of a material. For example, resistance is closely related to the cross-sectional area of the material and also the length of the material. So this is kind of intuitive, as you can guess. So if the cross-sectional area through which the current is flowing, if that is larger, then more particles can flow, right? So the obstruction to current is less. So the resistance is less if the cross-sectional area is larger. So this means that resistance is inversely proportional to the cross-sectional area of the material A. R is inversely proportional to A. If A is larger, R is smaller, and vice versa. Now, if the length of the material is also larger, that means a particle flowing through has to undergo many collisions before it reaches the other ends. So the resistance is larger. That is, the obstruction to current flow is larger. In this case, R is directly proportional to the length of the material. The two relations that we just discussed is R is inversely proportional to A, and R is directly proportional to L, L being the length of the material. And so you can lump these two relationships into one equation, and there is a proportionality constant that comes out, and this proportionality constant is called rho. Rho stands for resistivity. So this picture clearly shows this. So you have a material of length L that conducts current, and there is a cross-sectional area A, and so R is inversely proportional to A, and R is directly proportional to L, and the proportionality constant is given by rho. R equals rho times L over A, the ratio of L and A. So resistivity has SI units of ohm meters, and that you can see from the relationship. Resistance is in ohms, area is in meter square, and length is in meter. So resistivity has the units of ohm times meters. And there is another quantity that is useful in describing the current. It's called conductivity, and is denoted by the symbol sigma. Conductivity means how readily current can flow through a material. So conductivity sigma is given by the inverse of the resistivity, 1 over rho. So sigma equals 1 over rho. And it is important to note that the resistivity values vary from material to material. So the relationship R equals rho L over A holds for most ohmic materials, but the resistivity values, resistivity values may differ from one material to another. In this table here lists down some types of materials and shows their resistivities. This data is given for a temperature of 20 degrees Celsius. So you can see that conductors like silver, copper, and gold, they have very small resistivity, because these are metals, right? They conduct electricity very well. They provide less obstruction to currents. So their resistivity is very small, of the order of 10 to the power minus 8 ohm meters. Now if you look at semiconductors, which are not as good conductors as metals, but they kind of conduct electricity well, not that well, but kind of. They don't completely obstruct the flow of current. Current can still flow through them. Some examples are carbon, which is also based on the material graphite, or silicon, which is used in most of the electronics that we use. And you can see that their conductivity, their resistivities vary a lot. So carbon has a resistivity of 10 to the power minus 5 ohm meter, and silicon has something in between 0.1 to 60 ohm meter. And then we come to the third type of materials, insulators. These almost do not conduct any electricity. They block current very, very well. So their resistivities are very high. For example, you see in this case, glass has a resistivity of the order of 10 to the power 12, and hard rubber, which also does not conduct electricity, has about 10 to the power 15 ohm meters. It is also important to note that resistivity also is a function of temperature. In a conductor, resistivity increases with temperature. And why is that? Because if you provide, when you raise the temperature of the material, you provide more energy to the charge carriers and the atoms also. So the collisions become more frequent and stronger. The particles have more energy to collide. The number of collisions increase. The strength of each collision is also larger. The resistance, that is the flow of the particles in a specific direction, that kind of slows down. So the resistivity goes up, increases with temperature. So let us now summarize resistance and resistivity. So every ohmic material has a characteristic resistivity that depends on the properties of the material and on temperature. So that we saw in the table in the last slide. The resistance of a material depends on its geometry and its resistivity, right? The resistivity is different for different materials, and resistance depends on the cross-sectional area and the length of the material. So what is an ideal conductor? An ideal conductor means is one which does not obstruct current at all, basically. Current can flow through it really, really well, basically. So it has zero resistivity. In other words, it has zero resistivity. And what is an ideal insulator? An ideal insulator is the one that does not, through which basically current cannot flow at all. That means it has an infinite resistivity.